Data Science Analysis and Applications in Medicine Part 2, number 1562, the 6th of March 2026. Gerald C. EclaireMD Foundation. Category: Medical Data Science. Natural Intelligence and Artificial Intelligence. During my research process, I also realized an important difference between natural intelligence and artificial intelligence. These two forms of intelligence operate in fundamentally different ways, yet they can complement each other. The human brain functions through associative and parallel processing. When a scientist observes a dataset, multiple related ideas may appear almost simultaneously. Concepts such as waveform patterns, vascular stress, viscoplastic deformation, autonomic regulation, breathing control, and stroke triggering mechanisms may all emerge at once. The brain rapidly connects these ideas through a neural network of billions of neurons. This is what I describe as the neuron way of thinking. Ideas appear in clusters and often jump from one concept to another before a sentence is even completed. This associative pattern recognition allows the brain to quickly see relationships within complex datasets. Artificial intelligence, in contrast, operates more sequentially. AI systems organize information step by step, number by number, and equation after equation. They construct sentences and paragraphs in a structured logical order. This can be described as the computer way of thinking. Modern AI systems operate on multiple CPUs and large memory spaces simultaneously. As a result, their data storage and processing speed are excellent. However, they still lack the so-called intuition or sixth sense of the human brain. Often referred to as natural intelligence, the human mind can jump between ideas and automatically connect distant concepts. This ability to form spontaneous associations is what we commonly describe as human creativity. Each form of intelligence has its own strengths and weaknesses. Natural intelligence excels at pattern recognition, creative discovery, and generating new ideas. It also includes human empathy and emotions. Artificial intelligence, on the other hand, excels at organizing information, structuring explanations, and accelerating the writing process. It works best with tasks that rely on logic rather than feelings. In my biomedical research work, including psychology and personality disorders research, these two forms of intelligence work together. My natural intelligence generates insights from physiological data, while artificial intelligence helps organize these insights into structured explanations that can be communicated clearly. Idea generation and writing workflow. This difference between me and AI also explains the way I conduct my daily medical research writing. My brain often generates ideas very quickly, especially during quiet nighttime hours. Multiple ideas may appear simultaneously and jump from one concept to another before the previous thought is fully written down. Because these ideas often appear faster than they can be written down, usually capture them by copying and saving my ideas and conversations with AI tools in a separate note using keywords. This allows me to preserve the raw thoughts immediately before I forget them the following day. These captured ideas become the foundation for structured writing. Natural intelligence generates and interlinks the key ideas, while artificial intelligence helps organize these independent keywords or isolated thoughts into clear written articles that can be shared with readers. In simple terms, my daily research cycle often follows 4 steps: 1. Idea generation and paper structure through natural intelligence, my brain. 2. Idea capture through recorded conversations saved in an iPhone Word file. 3. Idea organization and extension, including validation of certain key points through AI-assisted writing and checking for knowledge production through completed articles using a combined model of me plus AI. This collaboration between natural intelligence and artificial intelligence allows creative insights to be preserved and transformed into organized scientific communication. Measurement uncertainty and stochastic analysis. Although natural systems may follow deterministic laws, measurements in the real world are never perfectly accurate. Sensors contain noise, instruments drift, and environmental conditions affect readings. These uncertainties must be considered when interpreting physiological data. For example, continuous glucose monitoring CGM devices provide valuable real-time information about glucose dynamics. However, these devices measure interstitial glucose rather than blood glucose directly, and they may sometimes display temporary instability or signal drift. For instance, during the first 1 or 2 days and the final 1 or 2 days of use, CGM data are often less reliable. If researchers treat every reading as perfectly accurate, incorrect conclusions may result. To address this issue, stochastic analysis can be applied. Instead of assuming that each measurement represents an exact value, the data are interpreted within an error band uncertainty range. Stochastic methods estimate the distribution of possible measurement errors and allow the researcher to evaluate the reliability of the signal. In my analytical framework, deterministic modeling remains the primary tool. Stochastic analysis serves as a secondary method that helps estimate measurement uncertainty. In other words, deterministic models describe the underlying physiological mechanism, while stochastic analysis describes the possible error surrounding the observed measurements. Applications to personal pathophysiological monitoring. The practical application of these ideas can be seen in my own long-term health monitoring system, using multiple devices and custom software. I collect high-frequency physiological data, including 96 glucose readings each day and 24 to 28 blood pressure readings taken daily. Instead of focusing only on average blood pressure, I analyze multiple aspects of the signal. These include pulse pressure as an indicator of vascular stiffness, SBP spike amplitude as a marker of rupture risk, and the dynamic variability of mean arterial pressure over time. By examining the waveform behavior of blood pressure, it becomes possible to detect patterns that may indicate increased vascular stress, which could lead to stroke risk. One example is the development of a stroke risk triggering sensitivity index, or TSI, which estimates the probability that a sudden blood pressure spike might trigger a vascular rupture in a structural weakened vessel. This type of analysis focuses not only on the magnitude of blood pressure, indicating vascular stiffness, but also on the dynamic characteristics of the pressure waveform. Conclusion: data science provides powerful tools for understanding complex biological systems when combined with engineering concepts such as viscoplastic energy, geometric topology, and stochastic probability analysis. Pathophysiological data can reveal patterns that traditional clinical observations often overlook. Equally important is the collaboration between natural intelligence and artificial intelligence. Natural intelligence allows scientists to recognize deep hidden patterns and generate new ideas instantly. While artificial intelligence helps organize and communicate those insights efficiently. The key insight is that biological measurements should be viewed as signals generated by dynamic systems rather than isolated numerical values. By collecting large longitudinal datasets and analyzing their structural patterns, researchers can better understand the mechanisms of disease progression. This approach transforms medical observation from static snapshots into continuous motion pictures of pathophysiological processes as data science continues to evolve. Such methods may help bridge the gap between engineering system analysis and modern biomedical research. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.